Okay, this is the second video it's the sixth, I think, or sixth or seventh in chapter 11, but it's the second one on molecular orbital theory, MO theory. I just kind of showed in previous video that how molecular orbital theory would describe the bond between two hydrogen atoms and also describe why the bond between two helium atoms, at least the uncharged ones, are impossible. Okay, so I'm going to take this further now and talk about the rest of the elements in the second row of the periodic table. So in the same way, so let's actually pick right up on. Let's look at the bond between two lithium atoms. Okay. So again, lithium, as you know, has a filled 1s orbital, but its valence electrons are then they have one each in the 2s. So what I'm going to do is I'm going to draw the, so again, each lithium has a 2s orbital. And these get mixed to form a 2s sigma orbital and a 2s sigma star orbital. Okay. All we did was we mixed these 2s orbitals together to form these molecular orbitals in the middle. Okay. One is bonding and one is the anti-bonding. So let's take a look at lithium. Well, lithium has one, each brings one valence electrons to the party. So we have one from this one lithium, two from the other. That's it. So look in the bond order. We've got 2 minus 0 divided by 2 equals 1. Sure enough, we would expect that diatomic lithium would form with a bond order of 1. Let's look at the next element, which is beryllium. And let's look at the type of bond formed in diatomic beryllium. All right. Beryllium is similar to lithium in that it has a 2s orbital, and of course it has 2 electrons that fills that. And when they mix to form molecular orbitals, we still have these same 2. But each has 2 electrons, so it goes 1, 2, 3, 4. And when we do our bond order calculation, you'll see it's 2 minus 2 divided by 2 equals 0. Meaning, essentially, diatomic beryllium does not exist and should never be observed, which happens to match up with reality. Okay. Now, so that's all fine. Now we actually kind of turn one last corner where we talk about the next element in the periodic table, which would be boron. Now, boron is a little different in that, don't forget, it has, in addition to 2s, it also has a 2p, right? Because boron brings 3 electrons to the party, and normally it would be 1, 2, 3. But when we mix these orbitals together, sorry, I need to draw them all 3 of these orbitals in. So again, there are 3 p orbitals and 1 s orbital. When we mix them, we're going to end up with 8 orbitals total, molecular orbitals, when you combine them. And let me actually draw what they look like. Okay, so 2 of them are, so one of them here is the 2s sigma, and then the 2s sigma star. Okay, and I just want to make sure I get the order right here. And I'm actually going to, well, I guess I should do it legitimately. Yeah. All right. Then we end up with with 2. Yeah, I haven't been drawing these right. I'm going to correct it right now. So I should be drawing this sigma 2s and sigma 2s star. That's actually the notation that the book uses. And the p orbitals will be the pi 2p. Okay, and then the 1 sigma 2p. Okay, and then the pi 2p star, and then that's 2 of them. and then the sigma 2p star, one of them. Okay. Now, just a quick little check. I'll make a comment about this. So here we're at the 2 level, and there's S and P. Again, we're talking about 2 atoms that are mixing their orbitals together because they're forming a bond. And if you think about it, each of these atoms are bringing 4 or bearing 4 orbitals together. When you add those 4 together, you'll end up with 8. And sure enough, 1, 2, 3, 4, 5, 6, 7, 8. We have 8 molecular orbitals that are a combination of the 2 different atoms orbitals at the 2 level. Okay. Now, you notice that we're using sigma and pi in the same kind of way that we used in VB theory, which is, remember in VB theory, there was a p orbital that is available for sigma bonding, usually hybridized. And then 1 or even 2, in the case of a triple bond, pi orbitals available for the pi type bonding, the side-by-side type bonding. So same terminology is used here. I don't think that's any accident, because I think there's an awful lot of common math that goes on between the 2 theories. So now I want to go back to our example again, where we're going to talk about boron, each bringing 3 electrons each. Okay, so boron, I'll use a different color because I'm going to erase the color. When boron fills this orbital, you'll see 1, 2, 3, 4, 5, 6. Okay, and when you do the math on this, the bond order will be the number of electrons in bonding orbitals, which happens to be 2, 3, 4, minus the number of electrons in anti-bonding, which happens to be 2, divided by 2, and you end up with 1. So the bond order of diatomic boron is 1, meaning it forms, and it forms a normal bond. Okay. All right, we can do the exact same thing with carbon. Okay. And now instead of 3 electrons, we're talking about 4. And it's going to be 1, 2, 3, 4, just like we saw, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, filling these. If you look at the bond order there, bond order is going to be 2, 4, 6, minus 2, divided by 2. That's 4 divided by 2. That's a bond order equal to 2. Essentially what that's saying is that when diatomic carbon forms, it forms a double bond. It's double bonded. It's stronger than a single bond. And sure enough, in your book, and if you look at Figure 11.21, you'll see I think you'll see the relative strengths, won't you? Well, it shows the bond order, but it doesn't show. It does. Yeah, it does. It shows the bond energy. There's a bar chart that shows the bond energy, and you see how that coincides with what we calculate here from our bond order. I'm going to continue this for nitrogen, which has 5. And what we're looking now is, what does it look like? What would N2 look like? Well, see, we even know that answer because we've seen N2 nitrogen a bunch of times. Well, let's see how the orbital theory predicts what we kind of already know. All right. Now, I do think I need to do. No, I don't have to do anything yet. I have to do a little trick here in a second, but I won't have to do that quite yet. So 5 electrons each. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's our 10 total electrons. Let's calculate our bond order for nitrogen. Number of bonds in bonding orbitals. Well, it's 2, 4, 6, 8. Number in anti-bonding. Did I do that right? 2, 4, 6, 8. Yeah. Did. seems like I've got this wrong. Y. Pi and sigma. Huh. Well, let me just continue with math. 2, 6, 8. Yeah. Oh, okay. Duh. Okay. Now, and the number of electrons in the antibonding is 2. Let's divide by 2. The answer is then 6 divided by 2, bond order of 3. What this says is that when nitrogen bonds together, it should see a triple bond. And we know that from the other theories that we studied, that's exactly what we expect, and therefore it is a strong bond that the figure depicts. The last thing, boy, am I going to be able to get it in? I'm going to hurry. I'm going to try to get this in. I'm going to do oxygen. The oxygen, I think I need to do the trick though, don't I? Pi, sigma. No, I guess I'm okay. I'm okay. Yeah, I'm okay. There's a little trick having to do with which energy level is really lowest. We're filling these orbitals in from lowest to highest energy. And there's a little bit of a bobble in there, and the book talks about it. But it turns out it's not that important, and I'm allowed to skip it. 6 each. What we're going to look for is, what does O2 look like? Well, we're just going to keep going. 1, 2. It's basically there's 12 electrons. 2, 4, 6, 8, 10, 11, 12. Let's calculate the bond order for oxygen. Number of electrons in bonding orbitals. 2, 4, 6, 8. Minus number of electrons in non-bonding or anti-bonding orbitals. 2, 3, 4. Divide that by 2. 4 divided by 2 equals 2. Oxygen should be a double bond. We actually know that. We've actually seen that, right? One really interesting aspect about this, though, before I'm going to gloss right by it, is the other thing that this theory predicts that the other theories don't, is that given that oxygen has 2 unpaired electrons in the molecular orbitals, means that oxygen, the diatomic oxygen molecule should be magnetic, and it is. And the other theories don't predict that. So this is actually one of the shining stars of MO theory, is it predicts that diatomic oxygen should be magnetic, and it is. The other aspect of MO theory is it predicts that certain molecules are impossible. And that's the other thing that's kind of interesting. I'm going to skip right to the end, which happens to be neon. Neon has 8 electrons. And we'll predict what the nature of diatomic neon should be. And again, we'll just continue this process. 2, 4, 6, 8, 10, 11, 12, 13, 14, 15, 16. 16 total electrons. Calculate the bond order. Number of electrons in bonding orbitals. 2, 4, 6, 8. Number of electrons in anti-bonding orbitals. 2, 4, 6, 8. Divide by 2. 0. Diatomic neon is impossible according to MO theory, and in practice we've never observed it. So, kind of the key takeaways of MO theory is that it's able to predict the magnetic properties of oxygen, which that's one of the interesting aspects. It's interesting to predict that certain diatomic molecules are impossible, and it predicts that very well through this mechanism that we've been going through. The other thing I mentioned is that the math is so complicated that beyond diatomic molecules that are of the same type, the homogeneous diatomics, like the ones we've been studying, once you go to even to 2 different atoms, the orbitals, when they mix, are mixed in complicated ways mathematically, and so this mechanism of filling orbitals from lowest energy to highest energy becomes harder. It gets even harder, way hard for complex molecules. So the theory is interesting, but it's fairly complex for anything beyond really simple molecules. Okay, that is the end of chapter 11 and the end of the first course in this book. So I'm going to end that here, and hopefully we'll start the second course here soon, which will start with chapter 12.